So I think if you're talking about conversion of energy, or how do we replace a lot of the energy we now use with cleaner, lower CO2 emission type processes, then if you look at what's available between wind and geothermal and solar, the really biggest part of the pie, if you will, is solar. And if you can actually combine the properties of both, that solar can, photovoltaics can harvest a lot of the high energy per quanta energy of the photons, so it has a very high effective temperature, something near the temperature of the sun, 5,800 degrees Celsius, versus the solar thermal, which goes down to about 600 degrees, and so it doesn't have that large temperature differential. And so really one of the exciting new areas is going to be combining photovoltaic style conversion, which takes advantage of the photovoltaic energy or the thermal energy, is really an exciting avenue. So another possible technology to actually extract electrons from the surface is not just using thermal energy to heat up these electrons and boil them off, and not just using photons to excite the electrons up to the conduction band and then migrate over to an electrode like in a photovoltaic, but using them together. And we call this the photo-enhanced thermionic emission process, or PEAT. And in this basic idea, photons come in, excite the electrons into the conduction band, and then you use the thermal energy to help boost those conduction band electrons over the vacuum level out to the cathode. Now the advantage is you get energy both from the photons to get the electrons into the conduction band in the first place, and also the energy, the thermal energy, to get them into vacuum. And so a lot of the loss from a silicon photovoltaic is actually that you only harvest that energy coming from the photon quanta, and then the thermionic only harvests the heat. But if you can harvest them both, your overall efficiencies and voltages can be much higher. However, one of the significant challenges to thermionics is just that you lose a lot of your voltage between the plates because there's so many electrons in the space between them that they start building up negative charge, just because you have all these charged electrons going through space, that it starts repelling future electrons from coming out of the surface. That's known as the space charge effect. And so that prevents you from getting really high efficiencies, and it's what limits current thermionic devices. So previously, everybody was looking for the lowest possible electron affinity that you could get, or work function for electron emission. And you do that by taking a material and you coat it with a low work function material, and you hopefully then get a low work function combination. And that works somewhat because the atoms that you add on are going to have low electron affinity. In other words, they're happy to give up their electron and be a positive charge on the surface, and that helps these electrons, which are negatively charged, hop out of the surface, because then they'll see this layer of positive charge. Now, more recently, what we've realized is not just metal atoms that can do this, but if you take something like a bit of diamond or some other material that may traditionally not have a low work function, and then you actually put it into an excited state. So you remove an electron from the carbon, leaving a positive structure behind, that is also highly charged, and then the electron can get out that way. In particular materials development, you want to have the ability to couple as much light into the emission surface as you can. And so we're exploring using nanocones and nanowires to actually absorb most of the light that is actually incident. And so it's amazingly good at absorbing the light, even for things that don't absorb very well, like silicon. And on the other hand, it can emit the electrons very well because of these very, very thin nanostructures, so that the electrons are going to be bouncing on the surface very, very often and have a good probability to escape. Once you're able to develop a technology that is able to bridge the gap between the solar temperature at 5,800 degrees C and kind of where most of thermal solar conversion cycles are operating around, say, 600 to 800 degrees C, you'd like to get something right in there that can take advantage of this huge temperature difference between the solar and that 800, 900 degrees C. And so if you can develop a high temperature conversion, maybe thermionic peat, you're in very good shape to put that device on top of existing concentrator systems, maybe power tower systems, or for parabolic dish concentrators, where you get a lot of light in a small volume, so you can get very, very high temperatures. Then you're going to get the efficiency of that high temperature conversion system, maybe 20–30%. And then on the bottom, you're also going to get the efficiency of the steam cycle, again, 20–30%. So your total efficiencies are looking at 40–50%. So what we hope to be able to do is develop a simple bolt-on platform that could go onto existing infrastructure that people are already building for solar thermal concentrated systems. And just have it sit on the front and then transfer its heat to the back, just like the normal absorber would have in those systems. So just replace the front absorber, and then we can see those going into the various solar farms and increasing the output per acreage, basically per unit of dish, by something like double what they're getting right now. Instead of 20%, we get 40% out of the same land. And so in terms of the dollars per kilowatt cost, it's much, much less. And with that kind of technology, you can actually start to approach coal and beat natural gas in terms of the cost of electricity.